Thanks everyone for coming to this semester's first seminar for the QFT and the mathematics seminar. Today we're really happy to have Vivek Saxena from Stony Brook and Rutgers, and he's going to tell us about homotopy of 2D SCFTs and an implication for TMFs.
Right. Thank you for the invitation and the opportunity to speak. So this talk is going to be based on a paper that came out sometime last year. That's the archive number. And it's going to be a physics talk. I should begin with a disclaimer that I'm neither an expert on homotopy theory nor TMFs. I'm going to only focus on a narrow physics application of some ideas to flow TMF classes. And this work, the ideas I'm going to outline really are based on technically intricate the work that a lot of other people have done. And I've just tried to follow them and give some physics interpretation. So my talk will mostly be about physical interpretations of things that perhaps people in the audience know or are well known to mathematicians. So I won't have anything deep to say about TMFs or homotopy theory in general. So basically the motivation is that as physicists, we would like to talk about the space of quantum field theories. And that's an ill-posed question. It's also intractable in general. But the idea of this program and the idea behind this talk is that if you restrict your attention to two-dimensional supersymmetric theories with minimal supersymmetry, that's these so-called n equals 0, 1, which means there is a right-moving supercharge, then you can make this question a little more concrete, and you can probe what's called the space of these theories. So based on some previous work and some ideas of Ed Witten, James Segal, worked on elliptic cohomology and made some connections to what's called the elliptic genus of a two-dimensional quantum field theory, supersymmetric quantum field theory. There was a proposal by Stolz-Teichner. I'm calling it the Segal-Stolz-Teichner program or the conjecture. It's not been proven to the extent that I understand it, but the statement is the following. So if you take some family of two-dimensional supersymmetric quantum field theories, they're characterized by an anomaly, it's an integer. It's an integer for the following reason, that there is the anomaly is characterized by an element. This may not be completely comprehensible to physicists, but it's a known fact from the work of Fried and Hopkins that it's characterized by the Anderson dual of spin bondism here in 4 dimensions. This thing happens to be isomorphic to integers. So this is what mathematicians would call the anomaly, because it's basically a mapping to the deformation class. And the statement is that if you take the set of families of two-dimensional n equals 0, 1 supersymmetric quantum field theories with this anomaly, the space is graded by this integer, and it's parameterized by some topological space X. So as a physicist, you can think of X as being some space of couplings with control parameters, which determines each point there will determine some family of field theories. And if you look at this set up to continuous supersymmetry preserving deformations, which is basically another way of saying this, that you're looking at homotopy classes of maps from this space of parameters X into this space of field theories, then Stolz and Teichner basically have said that this is isomorphic to what's called topological modular forms. That's a cohomology theory that was actually developed by Mike Hopkins, Haynes Miller, worked on by Gors and Lurie and many other people. I'm pretty sure I won't get all the references right, but some of them are listed here. So this was an effort to understand and extend what's called the Witten genus map in elliptic cohomology and extend it. So as I said, I won't really have anything deep to say about TMFs, except for the fact that it's a generalized cohomology theory. And I will think of it as a black box. It's some invariant. And the way this conjecture is set up, it says that TMFs are complete deformation invariants of CFTs, which means if you take SQFTs, if you take two field theories here, which are in the same deformation class, they will correspond to the same TMF class, which means basically, another way of saying it is that if you're given two field theories, T1 and T2, and they're both in this case, then the TMF class is agreed. But it also means that if you can't find the TMF class of one theory using mathematical methods, maybe spectral sequences or other technically complicated things. As a physicist, you might think of trying to go from this theory to this theory by some kind of continuous deformation that's preserved supersymmetry. And then you'll be able to say that the TMF classes agree. So you effectively computed, or at least reduced the problem of computing the TMF class to something that's already solved. And that's one of the things that basically this talk is about, reducing the problem to a previously solved one. So that's about as far as the result goes. In particular, in my talk, I'm going to only look at the ordinary version of this SST conjecture, where this space X is a point. So if you know something about E-infinity ring spectra, basically this means that you extract from the spectra, for any cohomology theory, any generalized Bordism theory or homology theory, you extract the homotopy groups by applying this operation. And it basically just says that the homotopy groups at level nu are capturing the information about the path-connected components of this space of field theory. So that was the thing that we wanted to understand. At the very least, to understand the space of field theories, you would like to understand its path-connected components first. So that's like the first point here to keep in mind. And it turns out that there is actually a abelian group structure on this space of theories. I won't describe it. Maybe this time I'll comment on it later. But so this is actually an isomorphism of abelian groups. So it's a well-defined notion. And one math motivation for this project, this physics project, was to ask the following question. What is the TMF class of a certain quantum field theory which lives at degree 31 in this cohomology? So this theory is in particular based on the current algebra of level 2 E8. So it's a two-dimensional field theory with a central charge, which is given. It's a purely bosonic holomorphic left moving theory. I'll describe it in greater detail and how it arises. And the idea was to compute it. And to my understanding, mathematicians believe that this is equal to the TMF class of another theory which has been studied, but there was no independent way of computing this. That's my understanding. If someone knows the answer to this, or if there's been greater progress, I'm very happy to learn more about it. And as I said, this talk was about reducing this to a previously solved problem. So the answer to this is going to be that I'm going to give you a physics argument to show that this TMF class is the TMF class of another field theory, which is derived from the level 1 current algebra. So just to remind you, if you have a compact Lie group, you can construct a two-dimensional conformal field theory by looking at the WZW model for some level K, and that's what we're doing here, except now there are two copies of it at level 1. The level 2 construction is a little more intricate, but it's been known. And the idea was to somehow get a handle on this, give some justification for this. That's one point. And the other point is that there's been some progress by Tachikawa, Yamashita, and collaborators, and maybe you've heard some of these ideas last semester. This TMF class actually lives inside a subgroup, it's actually a generator of a Z2 subgroup. And that Z2 subgroup comes from a certain map between TMF classes and ordinary KO theories. I'll get to that in a moment. I don't want to get ahead of myself, but the point is that I want to give physics justification for the fact that this also is the same, corresponds to the same generator. So as I said, this will be a physics talk. Occasionally, I will make some references to TMF results, which I'm certainly not an expert on. So please interrupt me if you think I'm saying something incorrect, or if you'd like to correct me. And the point is, I want to engineer these two theories using heterotic strings, which is a great source of two-dimensional CFTs. So a heterotic string starting in 10 dimensions is associated to that as a worldsheet 0, 1 theory, but it's a superconformal field theory. So one point that I didn't mention here is that these theories are not necessarily conformal. The ones that I'm going to talk about in most of the talk will be superconformal. So they'll be supersymmetric QFTs with conformal invariance. As a special case of these QFTs with conformal invariance will be non-chiral theories with a central charge C left times C comma C right. And in that case, this anomaly coefficient appropriately normalized with the difference of C left minus C right with -2. That happens to be a matter of convention, but it's important that that thing is. So when this happens, I'm going to restrict my attention to CFTs. So as I said, I'm going to try to give some motivation for this as from the physics point of view, and I'm going to first engineer these theories using heterotic strings. It turns out that they come from two 9-dimensional non-supersymmetric heterotic strings. It's been known for many years from the work of Ginsparg and Waffa in the 1980s. I'm not going to review the string theory construction, but since this map has to do with 2D CFTs, I'm just going to talk about the worldsheet. So from a worldsheet point of view, So from a worldsheet point of view, a d-dimensional heterotic string corresponds to a worldsheet CFT with central charge given by this. And this is the central charge. So there's if you compactify the heterotic string down from 10 dimensions to d dimensions, where d is something between 10, it's an integer, you get an internal CFT, which I call, say, T internal. And the rest of the degrees of freedom are captured by spacetime CFT, which has central charge. So I'll basically just focus on the first case. And in particular, if you take d equals 9, this becomes 17.3 by 2, looking at the first line. And I'm going to say that I'm going to look at two theories. The ones that I erased will be generated out of two worldsheet theories, which have this central charge. And as I said, I won't really use any string theory constructions except to say that these theories are well defined. So in order to introduce the worldsheet theories, I need to introduce some terminology and some. Let me do that very briefly. Erase this. So we follow some definitions just to understand the notation. So I'm going to use this notation to denote a compact boson CFT at radius r. So you should think of it as some scalar from the two torus. All the CFTs that I'm going to be interested in, I'll only study them on two tori. So this will be a map from a two torus to circle. It has a partition function. I'm not going to write down the expression unless someone wants to. It's a standard thing. It has central charge 1, 1. And its torus partition function has this property. Which is called D-duality. And this will be important for the talk. And in particular, this has a lot of symmetries. It has a U1 cross U1 symmetry, but I'm going to confine my attention to something called a half-period shift symmetry, which is a Z2 symmetry denoted by HP for half period, where X after period. So X is valued on a circle of circumference 2 pi r, and this is basically a shift symmetry. An interesting construction is to quotient this theory by gauge this. If you gauge it, you get a theory of a compact boson with half the radius. That's a well-known fact. So you might schematically want to write it as like so. This can be shown by looking at the partition function and decomposing it in the usual way, Z2 even and Z2 odd sectors. The second definition, so this is what I call as compact boson, just use this terminology. Then there's something which I will repeatedly say or assume, which is an n equals 0, 1 sigma model circle with radius r. That's basically just taking one copy of this along with a right-moving Majorana-Weil fermion, supersymmetrizing it. So this is like the right-moving superpartner for the right-moving compact boson coordinate. And this theory has a central charge 1/3/2. The third ingredients, I'm just quickly introducing things that are probably very well known to most people, only because I'm going to write them schematically later, is the R theory. This is a two-dimensional invertible spin theory. It's called the R theory because its partition function is based on the R invariant. So it's something which has a partition function on a 2 torus spin structure rho. So it's when the spin structures are chosen to be Ramon periodic on both one cycles and the torus, it's -1, and it's 1 otherwise. So basically what this theory does, we'll actually use it to fermionize bosonic theories and changes the space-time spin structure in an interesting way. And it also has fermion number symmetry. It's a fermionic theory. I might call it -1 to the f or C2R. And it'll play an interesting role. So with these ingredients, given any, we define something called fermionization. So if you're given a bosonic theory A with a non-anomalous C2 symmetry, you construct the fermionization of A. This theory is defined by taking the tensor product with the R theory, quotienting by a diagonal subgroup Z2, which is diagonal of this C2A times C2R. And the point is, as a theory in 2 dimensions, I'm just confining my attention to 2-dimensional theories. Eventually, they'll just be CFTs. So there's a systematic way of writing down the partition function, the torus partition function. Given the torus partition function of A, there's a way to write down the partition function of F. It's done very carefully, and it's a well-known fact in 2-dimensional CFT. Not going to review it, but I just want to define what this thing is. In terms of, with these 4 definitions, I can finally define the objects that I introduced at the beginning, which is this E8. So this is a purely bosonic theory. I frequently will use this term for it. So it's a 2D CFT. It's based on this current algebra. It has a central charge 16,0. It's purely bosonic, left moving. And it has a Z2 symmetry, which exchanges these two E8 level 1 factors. So that's going to be important. Finally, I define something called the E8 level 2 theory. Despite the name, it's not really a direct product of the E8 level 2 with this, but it appears like this in a very precise sense in the long distance of a string construction. So I'll maybe say something about it. This is simply defined as the fermionization of the E8 level 1 cross E8 level 1 with respect to the Z2 sigma that I introduced here. So you take the tensor product with the R's and take the diagonal. And it's a known fact in 2-dimensional CFT that you can construct there's a coset relation, which means that E8 level 1 plus E8 level 1. I'll explain what this means in a moment. If you take the quotient of these two representations, you get something which is the purely left moving theory for purely left moving Majorana wire fermions. So basically, this is the way you would construct an E8 level 2 in 2D CFT using this coset relation. It's a standard thing. It should be interpreted in the following way, that a state in a representation of the numerator can be written as a product of a state in the representation of this times state in the representation of this. So this is just what it is, and it's just the known thing in 2D CFT. So far, I've just introduced these things just to clarify the notation. The last thing that I want to do, or I will want to do, is given a fermionic theory, I want to gauge with -1 to Pf of fermionic theory. And this construction basically just means that if I'm given some bosonic theory, P bosonic, and I want to construct the tensor product of some little of it with a fermionic theory, and I want to construct quotient of this sort. So take the bosonic theory with the non-anomalous Z2 symmetry. This thing as a fermionic theory has a -1 to the F symmetry, and I want to basically quotient it by the diagonal. This is what I call gauging -1 to the F. So far I've just introduced things that are well known in QFT or CFT. I just wanted to be precise about what the definitions are. And the relation to TMF is going to become clear, but with these ingredients, I can finally define, and I'll leave them on the board because I might frequently refer to them later. And the two theories I'm going to construct or consider are, so psi tilde for me will always be a right moving Majorana wire fermion. This will be theory 1. Theory 2, find the T1 and T2 are in moment. Theory 2. And T1 is going to be a compact boson tensor product with gate level 1 times gate level 1, which was a theory I defined before, tensor with R.
Sorry, can I go back to
Yes,
page
please.
7?
Yes.
Tell again what gauging -1 to the F. Maybe I should say that is part of the spin group. Okay. So it's possible to gauge it in the usual sense without saying you're doing some kind of gravity.
That's a good point. So here, maybe if I say a little more precise. So supposing I start with here's what I mean. Maybe you can do it correctly. See, maybe I should write it more explicitly here before I go back. So let's say I'm given a fermionic theory. This is about 0.7. Try and address what Dan asked me. Let me see if I understand you correctly. So given a theory F, I have its torus partition function. That's what I mean. Now, the torus partition function first depend on choice of spin structure. And the point I want to make is that I want to turn on a gauge field, quote unquote, for -1 to the F. That gauge field will end up shifting the spin structure. Let's call that gauge field small a. So it will end up shifting the spin structure. And what I want to then do is think of this as a dynamical field, sum over it, which means I'm doing something like this with a sum over a, and in this case, general. So actually, I haven't really even used the fact that it's a torus. It's just some Riemann surface at this point, some thing on which F is well defined. And the resulting theory will have a background. In general, will also have a background fermion number symmetry. So let me call its background connection as capital A. So there's a dynamical connection that I'm summing over for a fixed rho. And there is a background connection A, which I call background. And also for a Z, for a -1 to the F. So Z2 group, if you like. It's like a, I guess, I suppose you'd want to call it a flat chirp. Like
It's a kind of.
it's
double
a,
cover.
pardon me?
It's a double cover. It's not a. It's a gerb or it's a double.
Well, I'm just thinking of it as a connection for -1 to the F. So it's a background connection for the Z2 symmetry.
Okay, keep going.
So now, so there's going to be some. So supposing I'm doing it on some Riemann surface, I'm going to have some pairing. I think this expression is well defined in terms of RF invariance. I don't remember off the top of my head what the precise form here is, but here is the general idea. And then I'm going to have a normalization, which is the sum of the number of spin structures. So this is what I meant by defining starting with an F, gauging -1 to the F. This is the operation that I'm talking that I mean. This is not my new background field. So let's say that now. Perhaps you can correct me as to what the precise meaning of this is, but this is what I meant by when I say I gauge -1 to the F.
It wasn't just summing over spin structures.
No. Summing over spin structures and summing over gauging fermion parity are not, as you know, not the same thing. It depends on the gravitational anomaly of the theory in 2 dimensions. They're the same if the gravitational anomaly is 0 mod 16. They're not the same if it's 0 mod 8. So here I just mean summing over these connections. And there's a fixed rho. So I'm not summing over, even though it appears that way because it's shifting the spin structure, but I'm not summing over rho.
So you start with a theory that depends on spin structure, and you
Yes.
get a theory that depends on both spin structure and double cover.
Yes.
That was a gauging process. And you
Well, this is what
background fields at the end.
Right, you have a background field A here. And just if you turn it off, you won't see the effect of this here. But you could in general turn on some gauge field. Maybe there's a more precise way of saying this, but this is the operation, perhaps the phrasing that is called gauging -1 to the F may not be quite the right way of thinking about it, but this is what I really mean. Since you asked, you just be more precise. So I start with the torus partition function of, so this theory, let me call it F tilde. So the torus partition function of F tilde as a fermionic theory on T2 is given by spin structures PQ, and that sum in this case looks like a sum over the holonomies for the Z2 gauge fields that I've turned down on the 1 cycles of the torus. So I take the bosonic partition function of this theory, which is in this tensor. It's graded by A and B. Those are the holonomies on the 1 cycles of the torus times this B plus A, B plus B. So the fermionic theory, that's the remnant of that rho plus A. That's kind of this is the precise operation which I call gauging. So given a torus partition function of a bosonic theory and a torus partition function of a fermionic theory, the final theory that I get has a partition function given by this. And certainly willing to concede that there's probably a better way of thinking about it, but this is at least my definition of what this operation is. Okay, so coming back to what I was saying here, I'm defining the 2 systems that I'm going to be looking at. So I'm going to take this product. So these 3 theories are separately described. I'm taking the tensor product, and I'm going to quotient it by the diagonal of the half period shift, which in this case is going to, if it were acting by itself on this, would shift it by from, if you were to just quotient it, you'd get a compact boson at radius r. And Z2 that flips the 2 EHs and Z2 of the R theory. So that's my theory 1. My theory 2 is going to be a compact boson at radius 2r prime, some other radius, and it's going to be this Fermianization of critical quotes, so that it's not really a product, times, that's it, sorry. And this I'm going to quotient from this. This I'm going to quotient. This is a fermionic theory, so it has a -1 to the F symmetry. This is where I needed that operation that I was talking about. So these are two worldsheet theories with central charge 17, 3/2. The 3/2 is we include this. And they are both theories with mu equals 31. And they, as superconformal field theories, they are both 0,1 superconformal field theories. And if you believe the conjecture which I raised, which is sort of the basis for this, they both represent classes in TMF -31, whatever those classes might be. And let me just give you a bird's eye view of what I want to get at. There is a physics argument which relies only on the comparison of the torus partition functions for these theories, which says that these two theories are T-dual, and the T-duality relies mainly on the T-duality between the compact bosons. It's not obvious here, and you have to write down the torus partition functions, explicitly compute them, which I have explained in the paper, but basically the idea is that if you take R prime equals 1 over R, these theories are T-dual, which means there is an equality of the torus partition functions, all four spin structures on the torus. So the first statement is result, P1 and P2 are T-dual. And as I said at the beginning, even though I didn't explain the details, these are really worldsheet theories for two nine-dimensional string theories, which are non-supersymmetric. These theories have a tachyon in space-time, but they are well-defined 2D CFTs, so we can work with them. And as far as the string theories is concerned, this really means they're essentially the same. If there's a duality relation of this sort, I can replace one by the other. If you believe that argument, which might trouble you in general, but if you believe it at the level of 2D CFTs, we're good. And these theories, the space-time tachyon can actually be detected if you look at the torus partition functions for each of them. And generally, the statement is that there is one space-time tachyon for each m. M is some integer, which is odd. So provided R, this radius that you're putting theory on, so this equality holds for R prime if you look at this theory, for R if you look at this theory, but I'm really going to only now be talking about this theory T2. So the result is that if the radius is sufficiently large, there is an integer m. The integer m appears in the partition function for the compact boson. I'm trying to give you a bird's eye view. If there are questions, I will get into the details, but I want to just get to what I'm trying to do here. Looking at the torus partition function for a compact boson at radius r, it can be written as a sum over momentum and binding modes. It looks something like this. Serial Q and Q bar. In my normalizations, looks like this. So in this frame, M is momentum and N is winding. And this is the theta function. And I'm doing this on the theory of radius R. And I'm saying that if you put this theory on this T2, compact boson on with R replaced by 2R, if you have an R that's large enough for a given M, N plays no role in this analysis. It's not obvious to say that from here. You have to do an analysis, but it's just some expression involving Q and Q bar Q series. You can read off the spectrum of the space-time theory by looking at the 2D CFT spectrum. That's a well-known fact because there's a state operator map. So for the space-time tachyon, that corresponds by the state operator map. Worldsheet tachyon vertex operator that would create the state. So for concreteness, let's set our eyes on P2 theory. This statement was true for the other one, but the analysis here is a little easier. So there's a tachyon vertex operator. Let's call it O. And the worldsheet is an n equals 0,1 sigma model. So if you add to the worldsheet action a deformation, which looks like this in superspace, if you like. This is 0,1 superspace. Theta is not important, but I'm adding this tachyon vertex operator as deformation. You can show, I can sketch the argument, but essentially you can show that adding this triggers an RG flow. So adding this tachyon vertex operator triggers an RG flow. And what I'm trying to get at is the fact that that RG flow will generate a potential. So in the infrared, we'll have a potential which looks up to a constant, looks like a cosine squared. So all this is done very systematically, but I just want to give a bird's eye view because so that we don't get lost in details. But the idea was to say something about TMF at the end. This potential gets generated by a standard exercise in 0,1 superspace. You can see that X is a compact boson coordinate. I've compactified one space-time coordinate in the space-time construction on a circle. So once you have this potential, it breaks U1 symmetry around the compact boson to a discrete Z mod M symmetry. So now what you have left is a Z discrete ZM symmetry. And because X is compact, the argument is that there are mod M vacua, absolute value M vacua. And if you expand the action, the worldsheet action around any one of these vacua, what you find is that the worldsheet degrees of freedom corresponding to the compact boson and corresponding to the additional fermions in the theory, they all become massive. And what you're left with is at each vacuum, you're left with only the degrees of freedom of this E8 level 2 current algebra. That's the in words what I'm trying to sketch. So this potential, adding this tachyon deformation triggers an RG flow. It's a relevant deformation provided R satisfies this inequality. It's large enough. So fix a favorite value of M. Add this deformation, triggers an RG flow, there's a potential, and just by an analog of the Higgs mechanism, you discover that these other fields in your theory, and this is the reason why this product notation is used, because in that limit, you find that this is generated by, this just consists of scalars. There is a current algebra construction consisting of 32 Majorana wild fermions, 31 of them contribute to this E8 level 2. Theory. One of them is the lone fermion. It gets a mass, and therefore the only thing that's left massless is this E8 level 2 theory. So if you accept this, what I effectively said is in summary is that I take my P2 theory, I add a tachyon vertex operator deformation. This goes to an RG flow. And I generate a potential. What I'm left with is just the E8 level 2 theory. And when I say this, what I really mean is the other degrees of freedom are massive. So at a scale that's set by this mu. Below that scale, I would treat them as massive. So the only massless degrees of freedom are this. As I said, this is a physics argument. It's not really a very precise math argument, but to the extent you trust CFT, this is what it means. Now, for physics reasons, which I didn't explain, but I said these theories are T-dual. So, in some sense, if you accept that T-duality is a valid operation in the space of, is a valid operation in the space of quantum field theories as a continuous deformation, these two theories are continuously connected by a sequence of T-duality and RG flow. Now, when I say RG flow, I should really say it in quotes because usually the physics argument is that you flow from the UV to the IR, which is sort of what I had in mind here. But I've really added some deformation, which doesn't break supersymmetry, breaks conformal invariance, but I could just also turn it off. I could just set mu 0. So that's why I have a double arrow here. This idea is not very precise the way I stated it, but there's a notion of going up and down the RG trajectories, which was due to Gayoto Johnson, and Edwin, where they essentially described a family of field theories as 0, 1, where you start with a 0, 1 theory, you add some supersymmetric mass information, kind of like what I've done, because that's giving things a mass. It flows to a theory tau prime, and then you supersymmetrically perturb it with some other theory tau prime. So these theories are continuously connected in some path of theories. Again, as I said, most of my arguments are physics-based, so there is lots of work needed to make this precise, but to the extent that you trust string theory reasoning, these theories are continuously connected. So I would, at the risk of being slightly potentially found rigorous, I would say these theories are homotopic. That's the title of that's what I really meant by when I said the theories are homotopic. So once you agree with that, and if you agree with what I had to say at the beginning, which was invoking the conjecture, it's clear that whatever the TMF classes are under the image of this Stolz-Teichner map, it must be the same. But not just that, there's another. So this is clear from that diagram, but what I really mean is that this is true with the Tachyon deformation, because it's a continuous deformation. So this was like a clever way, well, a physics way of decoupling the extra degrees of freedom, because you wanted to, remember the goal was to try to get the TMF class for this. To my understanding, mathematicians have not figured out a way to compute this without using this connection. And all that this is doing is reducing the problem to a previously solved one. So I haven't done any complicated computation. I've used results that people have already derived. In particular, I'm saying TMF classes of these theories are the same, but there's slightly more that can be said, which I think is interesting. So remember, from the physics side, which says something about TMF. Remember, this is the potential I erased, which I added, which came out of the, besides there's a 4, but it's not important. And I said that R has to be greater than M, and M has to be odd. So this is what I erased. This says something kind of interesting. So if you start with UV in general, if you start with UV, UD, n equals 1, U, 1, CFT, some degree mu. Imagine that when you flow to the infrared, you have some number m of vacua. So when this theory flows to the under RG flow, you have some discrete number of vacua. let's say that number is absolute value of m. I'm trying to connect to that picture. And at each of these vacua, locally, the theory is described by some theory X, which is an infrared description in the vicinity of this vacua. So there's like some sequence of theories X1 to X. Actually, let's just call this capital N. So there's a discrete number of vacua, and I have some n number of theories. There's a description like this. Now, if you trust physics, what physics is basically saying is at the level of TMF classes, the description of the TMF class of this should be reproduced by the sum of the descriptions here. So this is a slightly tenuous argument, but let me think it. So I claim that this is a good way to think about it. So here's the IR theory, and this is an equality of TMF classes, which I haven't computed. So this is very implicit. But here's the point: I should be able to recover all the information by looking at this description. So if I'm looking in the infrared and have n vacua, this is the description. TMF classes shouldn't change under RG flow. That was sort of the whole point. And now, if I apply this to this particular system, I have a system where I have a discrete m vacua. And if I started with my T2 mod psi theory, load in the RG, I have mod m vacua. At each vacua, the theory looks like a copy of E2, which is sort of the whole point of that Higgsing argument, that the description is just that of E8 level 2 theory. So what this means is that if you start with the TMF class of this, at each of these summands is the same, what we have is an equality of this sort. And I previously argued that these things are the same TMF classes for the full theory. I haven't actually given you a good argument for this equality, which is what I'm trying to get at. This TMF class is a class in TMF 31. Its generator, it's defined as x minus 31 in the literature, is an element of E2. Or rather, it's a generator of E2. I'll tell you what the Z2 comes at, but the whole point is this is therefore the same as the TMF class of E1. It's a class of Z2. No, it's generated by Z2. But that means the following: M is odd, so that must mean this must be a Z2 class. So this is what this argument tells you. That since M is odd, this is where we're kind of using the fact that there's a discrete number of vacua and that the number of vacua is odd. But that's a result that I got just by looking at the CFT partition function, adding that tachyon vertex deformation. And there's a very strict, if you read off the space-time spectrum, you'll find that this is the only way you can have it. And here I've just said that you start with this as the UV theory, quote unquote, you accept that physics reasoning, then the description in terms of TMF classes is just a sum of these TMF classes for each of these vacua, because that's the total description of the theory. Using the fact that M is odd, it means this, which means that it must be a Z2 class, since M is odd. So that's interesting because the generator of this is known to be a generator of Z2. Where these Z2s are really coming from is where you need to. So this was about as far as we got from this somewhat heuristic looking reasoning. When you erase this, since everyone's probably convinced that M is odd now. So at any degree, now I'm going to use the result from TMF, and I'm going to use it without justification or proof, but I have a physics way of thinking about it. So if I start with the homotopy group at degree nu, there is a map to KO, the KO spectrum of nu, which is the homotopy group of, maybe I should just think of uniformity, write it like this. This is a map induced from a map on the corresponding spectra. When you apply pi to it, the way to let's call this map phi. The way to think about it, or at least my way of understanding, is that there is a 2D CFT of 0, 1 type. It's represented by a TMF class, and this operation is extracting its elliptic genus, its partition function. In a particular sense, here's a Ramon sector partition function, and this describes its Q series expansion, where Q is equal to 2 pi r tau. There's a more detailed mathematical way of thinking about it. I'm not certainly no expert on this, but here's this result is important for us at degree 31, which is where these TMF classes live. And it's actually known that the image of this map, so is denoted by, let's just restrict to degree 31, the interest of time. It's known, so I call the image in the kernel as U and A. It's known that it's been shown by Tachikawa and Yamashita in using mathematical reasoning, using results on TMF, that this TMF class is a generator for this A minus 31, which in this case is a ZP. And if you look at the image of this, the image generates for you essentially the elliptic genus. As I said, if the image vanishes, the theory has what's called a 0 mod 2 elliptic genus. So in the interest of time, let me just say the elliptic genus is a generalized, it's like a torus partition function of this theory with the Ramon spin periodic spin structure. And there's in order to reconcile this map as a mathematical map, which was known to people working on TMF with physics, you need the generalization of the elliptic genus, because the usual elliptic genus vanishes under certain conditions. This happens to be one of them. So there was a notion of a mod 2 elliptic genus, which is due to these authors and also due to Barrow and John's third. And the idea is the following, that you take your favorite theory, your TMF class, you take the image and you get the mod 2 genus, elliptic genus. It's like a mod 2 reduction of it. And if what I said here is correct, this theory should correspond to the theory that lives here in the kernel, so that its mod 2 genus vanishes. And there's an independent way of checking that by looking at the partition function for this theory. And if you look at that partition function, it has only even coefficients. In the interest of time, I can, but let me not spell out what that series expansion is. But using just physics methods, you can write it down. And once you write down, looking at the character expansion for this, you see that all the coefficients are even, which means the mod 2 genus vanishes. So it's a confirmation of that somewhat heuristic level of reasoning. But this is, of course, a more systematic way of thinking about it, if one is sophisticated enough to derive this. So in conclusion, all I've done is I've given you some physics arguments to show that this class is the same, this class and this class are the same. If you believe that at the beginning for some other mathematical reasons, then of course this didn't add much value, but it's a nice way of thinking about it, I think, because what I ended up showing was that these theories are homotopic, quote unquote, continuously deformable into each other using that tachyon vertex. One interesting thing that I found, of course, one future direction would be to extend it to other degrees. That's a natural thing. I only looked at these specific CFTs, but the heterotic string constructions, especially the non-supersymmetric ones, there's like lots of things that one could do, and that's an interesting extension, but that's like a matter of detail. But one conceptually interesting thing that I found was, in this case, each theory and the discrete vacua is the same, but in general, you could have theories which are different. They all have the same degree. It might be interesting to look at situations where this UV theory fractionates into different discrete theories. So that's something that I'm thinking about. But that, thank you.
Do you have any questions in the room? You mentioned the heterotic string construction. What was the benefit of using that, or just knowing these theories otherwise?
The way I wrote them, I didn't really use the heterotic string construction, but these theories are not new in the sense that people in the 90s have looked at them, classified different heterotic strings. This is just one of them, a pair of them. But this way of writing definitely makes it more clear as to how to get connection to TMF. I mean, the point is, if you know direct these product operations, they map to product operations. Some operations map to some operations. But this is like a gadget in itself. I mean, it's not clear what to do with it. So so for your favorite heterotic construction, you could write down the corresponding worldsheet CFT. If you understood it in this language, which I guess you can, at least some of them, most of them can now be thought of in this language, then you could make some connection. I just use the heterotic string to motivate the fact that that's one realm in which lots of interesting 0, 1 CFTs appear. But the other connection, which I didn't say anything about, was the work of other people, some of which is cited here, which is that they were using this argument that the Segal-Stolz-Teichner thing is a theorem and not a conjecture. Use this argument to show that, or argue that the global anomalies in the heterotic string vanish. So for them, they restricted their attention to those CFTs which are worldsheet CFTs of the heterotic type. We computed the anomalies and some classes which vanish. So there it's relevant to, there the heterotic connection is definitely relevant.
Any more questions? Any questions over Zoom? Oh, well, if not, let's thank you back again.
Thank you.